Okay, so using that two-step process that we just described, let's look at an example of calculating the heat produced in a calorimeter using this two-step process. So, here's an example problem. We have an experiment to determine how much calorific value, or basically the energy content, of a sample of food. It says we burn it in a calorimeter in an oxygen atmosphere, and the temperature rose by 5.2 degrees Celsius. When a current of 1.27 amps was passed through the same calorimeter from a 12 volt source for 10 seconds, the temperature rose by 2.5 degrees. Calculate the heat produced by the combustion of the food. So anytime we see a problem that we can identify as a calorimeter problem, we have to identify the temperatures that are associated with calibration of the calorimeter and differentiate that temperature change from the temperature change that is associated with the actual reaction. So our problem here tells us that when we burn the sample of food in the calorimeter, we get a temperature rise of 5.2. So therefore we know that this 5.2 degrees Celsius is associated with the reaction that was for the combustion of the food. On the other hand, we see that the problem tells us that when we flow this current through a 12 volt source for 10 seconds, the temperature rose by 2.5 degrees. So we can therefore associate this temperature increase with the calibration of the calorimeter. So now that we know that, we can approach our two-step process using this information. So the first thing we have to do is the calculation for the calibration of the calorimeter. Alright, so basically we're trying to determine the calorimeter constant, C, which is the heat capacity of the calorimeter, Q divided by delta T. In this case, we know that Q is equal to the current times the voltage times the temperature, and we can therefore substitute current voltage current voltage time. This is Q is equal to current times voltage times time. And we also remember that the current is supposed to be in a unit of amps, the voltage is supposed to be in volts, and the time is supposed to be in seconds. Amps times voltage gives us coulombs. A coulomb second is a joule. So just reminding us of that. So after we finish with the substitutions in this equation, we can take the current in amps, 1.27 amps, times the voltage, which is 12 volts, times the time, which is 10 seconds. And let me make sure you can read this. Let me rewrite this. Sorry. Alright. Current 1.27 amps. Voltage 12 volts. Time 10 seconds. And the temperature change associated with this is 2.5 degrees Celsius. And remember that degrees Celsius and Kelvin are interchangeable when we're talking about a temperature change. And so 1.27 times 12 times 10 divided by 2.5 gives us 60 60.96 joules per degree Celsius. So that is our heat capacity of the calorimeter, C-cal, whatever you want to call it. So now, step 2 of our process tells us that we're going to use this heat capacity for the calorimeter to actually calculate the amount of heat that was generated when we burned the food. So step 2 is we're going to take this C value and determine heat. So rearranging the equation to calculate our heat content, we're going to substitute this value into here because that's from step 1. So 60.96 joules per degree Celsius, and then the temperature rise associated with this reaction is 5.2 degrees Celsius, and therefore our heat generated by our reaction is 316.99 joules because our degrees Celsius cancel. And so that is how we calculate the heat generated in a calorimeter experiment. Step 1 was to use the data for calibration of the calorimeter and calculate the calorimeter constant or heat capacity of the calorimeter. Step 2 is to use the heat capacity of the calorimeter and multiply it by the temperature change that you get when you actually do the reaction that you're interested in, and that gives you the heat output. Now that I know this calorimeter constant, it doesn't matter what experiment I do, any temperature increase I get, I never have to repeat this calibration again until, of course, we're going to calibrate a calorimeter in the lab setting on a regular basis. But for our practical purposes, we don't have to repeat this calculation anymore. We just use the calorimeter constant to plug in, and all we have to do now is look for a temperature change, because whatever the temperature change is, we're going to multiply that temperature change by the calorimeter constant each time. For example, if I did another reaction and I ended up seeing a temperature change of 2 degrees Celsius, all I would have to do is multiply 2 degrees Celsius by the calorimeter constant, 60.96. And I would end up with 121.9 as my heat output. So that's an example. We're going to do one more example just to make sure we got the point across and the message is driven home. Okay, this one says a sample of a Twix candy bar, this is supposed to be Twix, was burned in a calorimeter and resulted in an increase in temperature from 22 degrees Celsius to 50 degrees Celsius. When a current of 5 amps was passed through the calorimeter at 10 volts for 100 seconds, the temperature rose by 3 degrees Celsius. How much heat did the sample of Twix generate? So we're going to do the same process. We're going to identify which temperature is associated with calibrating the calorimeter. So we know that when the current flows through the calorimeter, we get the increase of temperature for 3 degrees Celsius. So that 3 degrees is the temperature that's associated with the calorimeter constant, or the calibration of the calorimeter. And on the other hand, the 22 degrees Celsius is the temperature change that 22 to 50 degrees Celsius is the temperature change that we get when we burn the sample of candy in the calorimeter. Okay, so once again, step 1 is to determine the heat capacity of the calorimeter, or calorimeter constant. I'm just going to skip to this part since we already showed the justification for this in the previous slide. The current is 5 amps. The voltage is 10 volts. The time is 100 seconds. And the change in temperature is 3 degrees Celsius. And when we multiply our 5 times 10 times 100 and divide that by 3, we get 1,666.7 as our calorimeter constant, and that unit is in joules per degree Celsius. Step 2 now is simply to take the temperature change associated with the reaction and multiply it by the calorimeter constant. Take this calorimeter constant and substitute it, and we get 1,666.7 joules per degree Celsius. That's pretty big. I made this problem up. And then we get the delta T, which is 50 degrees Celsius minus 22 degrees Celsius, which is 28 degrees Celsius. And when we simply multiply those two together, we get a heat output of 46,667.6 joules for that sample of candy. Very simple. Step 1, calibrate the calorimeter, calculate C of that. Step 2, use that C and multiply it by the change in temperature to get your heat output. Now here's an example problem for you to do. When we have 10 grams of a Krispy Kreme donut burned in a Bond calorimeter, the temperature inside the calorimeter increases by 23.2 degrees Celsius. When a current of 1.5 amps was flowed through the calorimeter through a 12 voltage source for 60 seconds, the temperature increased from 25 degrees Celsius to 29 degrees Celsius. Calculate the energy content per gram. You're going to do step 1, which is calibrate the calorimeter, determine C of the calorimeter, and for number 2, you're going to use that calorimeter constant and the temperature change you got from the Krispy Kreme donut. And in the very end, you're going to do one additional step, which is divided by the mass. Whatever energy output you get, the heat output, you're going to divide that by the mass, which will give you energy content per gram. Work that practice problem on your own to convince yourself that you can do it.